Hey, welcome back everybody. It's even colder today than it was yesterday. So we might as well keep talking about friction. Yesterday we were learning about the mathematical explanation of this fun equation. Friction is fun, you know that. Okay, so now we're going to look at doing a couple more problems with it. So yesterday we talked about when it would be maxed out and when it wouldn't be maxed out on, like, let's say, a ramp, right? Okay, so we showed a lot of explanations on a ramp, but the same thing. If our max friction is 10 newtons, and we have a box like this, and I have a force of a push of 8 newtons, what is friction in this case? 8, right? And we said that a little bit yesterday, but we got into the ramp so much that I almost wonder if we kind of forgot about this, the more simple stuff, because I tend to do that a lot. So this formula works for everything, not just the ramps. So today we're going to actually look at what happens with some problems here. So the first problem we have is this, okay? So we got 10 kilogram mass, and it's being pulled with 20 newtons. The question is, what's the acceleration? Okay, so this would be frictionless. Can you figure out the acceleration here? Give you a little warm-up. Yes, that's right. It's 2, right? Because the summation of forces cause the mass to accelerate. Accelerate is summation of forces divided by mass. In this case, it's 20 newtons. Now you might be thinking, well, what about gravity, right? Well, that's the force of gravity. But what's counteracting that? The force normal. So those two, the summation of forces in that direction is 0. But the summation of forces in the horizontal here is 20 divided by 10. My acceleration is 2 meters per second squared. Can you do that? Okay, here in our next situation, we have, again, no friction. Okay, so we're starting without friction. But we have a tug at an angle, 35 degrees. Okay, so the part that's going to accelerate this, unless, so we're going to break this up into x and y stuff, right? So maybe that would be the first thing we would do. So the cosine of 35 times 20 is what? 16.38 newtons. And the sine is 11.47. Thank you very much. I appreciate that efficiency. Okay, so I want you to kind of pay special attention to this right here. This one right here. If that is more than the force of gravity, you're going to be pulling that thing off the ground. Right? Now this is going to be 100 newtons, right? So that's definitely more than the 11.47 that you're tugging up on it. But what is this going to do then? Is that going to change anything, any of the forces that we've talked about earlier? Exactly. It makes the normal smaller, because the two definitions of the normal are they're perpendicular to the surface that the object's resting on, and it's the force the surface applies to keep it from falling through the surface. So in this case, then the force normal is going to be, what, 98.53. 88, I'm sorry, 88, thank you very much. Well, it's 100, and then minus this y help right here. Okay, so it's 88.53. Now, do we need to know that for this question? No, we don't, but we will later when it gets a little more fun. Right? So this would make a difference if we had friction. In this time, it doesn't make a difference. But we need to know this, because this is the force that's going to cause this thing to accelerate horizontally. So the acceleration in this case would be 16.38, because there's no other force in the horizontal, divided by 10, or the acceleration here is 1.638 meters per second squared. Can you do that? Okay, here's our next question. We've got tension at 25 degrees with a tug of 30 newtons to up and to the right. And then we have our frictional force, which is going to fight against the movement, right? To the left. Question again is, what is acceleration?
Change in velocity.
So the first thing we got to do is figure out this piece and this piece. So the cosine of 25 times 30 and the sine of 25 times 30. Okay, so now that we have our parts of the vector in the x and the y direction, we can start this, right? So the first thing we've got to realize is that we still have 100 newtons here for weight. So this is not going to pick it up off the ground, but like Chandler said earlier, it is going to alleviate the normal. But the only problem is, or the only thing is, we don't really need to do that yet because I've already given a frictional number. Okay, so now we can see that we have a force of 27.19 points to the right, and then we have friction point to the left. So our summation of forces this time, which will cause the acceleration, is going to be 27.19 minus 2 divided by 10 kilograms. So our acceleration is 25.1 or 2.5 meters per second squared. Can you do that? Okay, here's our next little situation right here. We've got a tug of 110 to the right on a 10 kilogram mass. We do have a coefficient this time. We're trying to find the acceleration. Okay. So we can look right here to know that acceleration is summation of forces divided by mass. And in this case, the summation of forces is 110 minus the force of friction divided by 10. Right? So 110 minus the coefficient times the normal, which is 0.256 times 100 for the normal, all divided by 10, will give us our final acceleration. Okay, so we can tell that friction is 25.6 in this direction, opposing that motion. Okay, and it's the coefficient times the normal. Okay, so our acceleration then is going to be 110 minus 25.6 divided by 10 is going to be like 80 or 8.56. 8.44 meters per second squared. Can you do that? Okay, here's, this is probably the biggest level of difficulty of these types of problems for us. The question here is the acceleration. So the first thing we have to do is resolve our vector into x and y. Okay, so the sine of 35 times 90 and the cosine of 35 times 90 are 51.62 newtons up and 73.72 newtons to the right. Thank you, Hayden. Okay, so now this time we're going to have to know how the effects of the normal come into play here. Okay, so we know here that normal is 100 newtons, weight is, but the normal is going to be less than 100, so I should probably draw my arrow smaller or bigger. The normal is going to be less than 100 because it's getting pulled up on over here by 51.62. So now all the surface has to apply to keep that thing from falling through is going to be 48.38. So the force normal here is 48.38. And how we got that? Well, we took 100 minus the 51.62 that the rope was pulling up, and then we got our force normal. So now we can go ahead and figure out our acceleration. Okay, so our acceleration is the summation of forces divided by mass. And the summation of forces is 73.72 right here minus the force of friction, right? Because friction is going to have to be going in the opposite direction. And all that is going to be divided by 10 kg. Okay. So 73.72 minus 0.333, which is our coefficient, times our normal, which is now 48.38. It's our normal because we had that tug up to help alleviate that weight. All divided by 10, and we get our acceleration then at 5.76 meters per second squared. Can you do that? Okay, so that concludes friction video part 2 and the fun formula.